Hello again. In this section of the tutorial, we are going to talk about individual fairness and clustering. So without further ado, let's begin our discussion. So far, we have only talked about concepts of demographic fairness, whereas it became evident the high-level goal is to treat each group of points fairly with respect to either how other groups are being treated or with respect to the specific needs of the group at hand. Now, in individual fairness, our attention shifts from groups to individual points, and therefore the high-level goal becomes treating each individual point fairly, again with respect to either how other points are being treated or with respect to the specific needs of the point at hand. The question that naturally arises here is, doesn't demographic fairness imply individual fairness if, for instance, we view each point as a demographic group of its own? Well, let me say that this is a great question. However, I'm going to argue now that all concepts of demographic fairness that we discussed become vague or are not well defined in this context, in the context of singleton demographic groups. And let me give you some examples that demonstrate this. At first, recall the notion of balance, where the high-level goal is to seek solutions where, for each demographic, the fraction of its points inside every cluster should be the same as the fraction of its points over the whole dataset. Now, if we are to apply this notion of fairness in the case of singleton demographic groups, we see that there is only one feasible solution to such a setting, and this feasible solution is a trivial one. Namely, this trivial solution is create a mega cluster which includes all points of a dataset. Therefore, there's nothing interesting here. Another example of a concept of demographic fairness that fails in the case of singleton demographic groups is proportionality. So here, recall proportionally fair clustering, where the high-level idea is that groups of points that are large enough should be entitled to their own cluster center. If we are to translate this concept of fairness in the case of singleton demographic groups, what we have is that each point should be entitled to its own cluster center, or in other words, every point should be a cluster of its own. However, since in all applications, the number of clusters we can create is far smaller than the number of points in the dataset, we see that in this scenario here, there doesn't exist any feasible solution, and therefore, again, nothing interesting to study. Finally, let's see what happens to the socially fair K clustering problem in the case of singleton demographic groups, and recall that the objective in the socially fair K clustering model is to minimize the maximum average assignment distance over all demographics. Now, if each demographic group contains just one point, we see that the objective of socially fair K clustering is equivalent to minimizing the maximum assignment distance over all points. And this is exactly the case center problem. Therefore, in the case of singleton demographic groups, socially fair K clustering reduces to something that is already known, and therefore nothing interesting, nothing novel in studying this case. Therefore, we come to the realization that demographic fairness cannot adequately capture the perspective of individual fairness, and hence, if we are interested in identifying meaningful notions of individual fairness for our problems, then we need to somehow change our mindset in how we approach modeling such fairness considerations. Before I proceed to actual concepts of individual fairness, I would like to say a few words about the seminal work of Dwork et al. For those of you that are not familiar with this work, this is basically a very fundamental work in the area of individual fairness. And specifically what Dwork et al. Did in their ITCS 2012 paper is introduce a very elegant and a very well-justified model for individual fairness in the context of classification. Now, the high-level goal behind the concept of fairness introduced by Dwork et al. Is summarized in this sentence over here, which is similar individuals should be treated similarly. I will not go into further details regarding the work of Dwork et al. All I want you to keep from this slide is this sentence over here that summarizes the high-level concept of individual fairness in this work. The reason I'm mentioning the Dwork et al. Work now is because it will help us in creating a taxonomy of concepts of individual fairness for clustering. And specifically, we are going to make a distinction between concepts of fairness that follow the Dwork et al. Paradigm and concepts that do not. So let's begin with concepts of individual fairness and clustering that follow the Dwork et al. Paradigm. As I mentioned a few seconds earlier, the high-level goal here is to treat similar individuals similarly. Okay, now, if we are to transform this abstract concept of fairness into rigorous and well-defined clustering problems, we need to answer two questions. The first question is, how can we define similarity between points in a clustering problem? So basically, you see that the first question tries to interpret this part of the definition. The second question is, how can we interpret similar treatment in a clustering setting? And the second question tries to interpret this part of the definition. And obviously, different answers to these two questions will yield different individually fair clustering problems. I want to argue here that the first question is actually not that important from a fair clustering perspective. And this is because defining similarity between individuals, between points, is more of a modeling issue. Therefore, we can always assume that there is some higher all-knowing authority that will give us the true similarity relationship for the points. On the other hand, what is far more important is the second question. And this is because here, defining similar treatment is equivalent to defining fair treatment. Given this realization now, that is that the second question is the more important one, we will further classify concepts of individual fairness and clustering that follow the Dwork et al. Paradigm. We will classify those based on how they answer the second question, based on how they define similar treatment. Now, let's begin with the family of concepts of individual fairness and clustering that follow the Dwork et al. Paradigm. And these concepts here define similar treatment in terms of trying to place similar points in the same cluster. I would like to begin with a motivational application, with a motivational example that demonstrates the sort of fairness considerations that we want to address with these concepts. So, suppose that we have the employees of a company, and suppose that we also have their performance rating for the current year. And let's assume that the company wants to cluster its employees into K groups based on their performance rating. And let's assume that after the clustering is created, the company will decide the specific ordering of those clusters such that the people in the first cluster will receive the highest amount of raise in the next year, the people in the second cluster will receive the second highest amount of raise, and so on. So this is the application at hand. In this context, let's assume that me and Seyed are two similar employees. That is, we have comparable performance ratings. And suppose that the clustering solution places Seyed in a cluster that receives a much better raise compared to my cluster. If that's the case, and I'm able to perceive our similarity, to see our performance ratings, I have every right in the world to feel unfairly treated. And this is because I can tell that we are similar employees, and yet I cannot justify the company's decision to give, say, a better raise than me. So this is exactly the sort of scenario we want to address with this family of concepts. And you can see that in such scenarios, what matters, what is important, is placing similar points in the same cluster. Now it's finally time to discuss an actual concept of individual fairness for clustering, a concept that follows the Dwork et al. Paradigm. And this concept here defines similar treatment in terms of trying to place similar points in the same cluster. This concept was introduced in an ICML 2020 paper, and actually most co-authors of this paper are also organizers of this tutorial. Let me begin by telling you how we resolved the modeling issue of defining similarity in this model. Okay, basically what we did was assume that for every pair of points, we are given a value psi in 0, 1 that indicates the true similarity of the 2 points, and the smaller the psi value is, the more similar the 2 points, with 0 indicating absolute identity and 1 indicating absolute dissimilarity. The reason we chose this way to define similarity between points is because this is exactly what Dwork et al. Do in their seminal work. I also want to argue that this value psi can actually be significantly different from the metric distances d. And there are multiple reasons for that. The first reason may be that the metric distances may encode redundant features such as race or gender, features that we do not want to take into account in a fairness-oriented application. Another reason for why psi and d may be different is because psi may measure similarity, but similarity as perceived by the individuals. And therefore, if we want to make the individuals happy, then we should seriously take into account the way they perceive their own similarity to other individuals, instead of just relying on some experts' advice, which might be reflected through the metric d. Another reason for why psi and d might be different, and I don't have this in the slides here, is because there are applications in which the function d measures physical proximity in a metric space, while the value psi may measure similarity with respect to some underlying fairness consideration. And my point here is that physical proximity does not necessarily imply similarity. Okay, now let's move on to how exactly we define similar treatment in this model. Okay, for this, recall the motivational example of clustering the employees of a company, and recall the unfair scenario that might arise there, that is Seyed getting a better raise than me. The question is, how can we mitigate such a scenario of unfairness? To answer this question, we stopped and thought for a moment, and we saw that for 2 points that are relatively similar according to the psi values, deterministically separating the 2 points, that is, deterministically placing them in different clusters in every possible return solution, doing that sounds like a bad idea. And therefore, our way of introducing fairness in this context is through randomization. And specifically, we are going to seek solutions that cluster the 2 points apart with probability at most a given psi value. Okay, so here, note that the more similar the 2 points, the smaller the psi value, and therefore the less likely it is for the points to be placed in different clusters. The formal problem definition goes along the following lines. At first, we need to choose a set S of at most k cluster centers, as always. But here, we do not simply ask for a single deterministic assignment function. We rather ask for a distribution D over assignments, and we want this distribution to satisfy the following important property. This is basically the property that captures the notion of fairness that we aim to study. This property here says that for every pair of points, you should make sure that the probability that a randomly drawn assignment separates the 2 points is at most the given psi value for the points. Finally, we might also want to minimize some metric-related objectives such as k-center, k-median, or k-means. Okay, as I mentioned, we introduced this model in an ICML 2020 paper, and in that paper, we only studied the model for under the k-center objective function. And for that objective, we gave a log k approximation algorithm. However, this algorithm does not work for arbitrary psi values. It only works when the psi values have a specific structure, namely when the psi values are an increasing function of the metric distance. Nonetheless, even if this algorithm has a relatively large approximation ratio and doesn't work for arbitrary psi values, there is still some merit to it. And there is merit to it because At first, this is a very efficient algorithm, very efficient in terms of its runtime. And also, the solutions produced by this algorithm are guaranteed to have a bounded price of fairness. Later on, in a paper that appeared at AAAI 2021, we again studied this model, and in this paper, we gave constant factor approximations, and these approximation algorithms, this approach, the approach of the AAAI paper, can also handle k-median and k-means, not just k-center. Perhaps most importantly, the approach of the AAAI paper can also handle arbitrary psi values, not just psi values that are an increasing function of the distances. Nonetheless, these benefits come at the expense of efficiency, and the AAAI algorithms are not that efficient in terms of the runtime compared to the ICML algorithm. And they are, of course, polynomial time algorithms, but they are not efficient, and they are not efficient because they are based on linear programming, and the linear programs that we use are quite large. Now I would like to briefly discuss a related concept of individual fairness, a concept which also follows the Dwork et al. Paradigm. And again, this concept here tries to define similar treatment in terms of placing similar points in the same cluster. This concept was introduced by Anderson et al. In a 2020 paper, and I will begin by telling you how the authors here define similarity between points. Basically, what they did is exactly what we did in our work, in the work we were discussing just now. That is, they used the approach with the psi values. And I am certain that they did that because this is what Dwork et al. Do in their seminal work. Let's move on now to the computational goals of this model. At first, as always, you need to choose a set S of at most k cluster centers. But this time in this model, for every point j of the dataset, you need to compute an assignment distribution phi j over the set of chosen cluster centers. And this assignment distribution will actually give you the probability with which the point will get assigned to each of the chosen centers. Okay, let's see now how Anderson et al. Defines similar treatment, how exactly they define similar treatment. Before we proceed to that, some notation. Suppose that we have a metric D that captures statistical proximity, and examples of such metrics are the total variation or the KL divergence. And now, according to Anderson et al., similar treatment is defined as guaranteeing that for every pair of points, the statistical proximity of the computed assignment distributions for the 2 points is at most the given psi value. And now you can see that I actually told you a small lie, a small white lie, when I mentioned that this model defines similar treatment in terms of placing similar points in the same cluster, in terms of giving the same assignment to similar points. There is a subtle difference here, and that is that this model defines similar treatment as providing similar assignment distributions to similar points. At first glance, this model might appear as similar, very closely related to our model, the one we were discussing earlier. However, there are significant differences. The first difference, which is not really that important, is that in our model, the final outcome is an actual assignment of the points to the cluster centers. The final outcome is an actual clustering, a clustering that we draw from our constructed distribution. In the model of Anderson et al., the final outcome is a collection of assignment distributions, one distribution for each point. The most important difference now comes in how the 2 models perceive and define similar treatment. In our model, similar treatment is defined as upper bounding the separation probability for any 2 points. And recall that the separation probability is the probability with which the 2 points will be placed in different clusters. In the model of Anderson et al., similar treatment is defined as upper bounding the statistical proximity of the computed assignment distributions for the points. And these 2 things are completely different. So let's see an example that demonstrates this. In this example, we have 2 points, j and j prime. And suppose that in the model of Anderson et al., we have computed 2 assignment distributions, one for each point. And let's also assume that both of these distributions are the uniform distribution over the set of chosen cluster centers. Then, According to the model of Anderson et al., we have achieved absolute fairness. And this is because the statistical proximity between the two distributions is 0. However, from our perspective, from the perspective of our model, let's see what happens there. Okay, in our model, if these two distributions, Fj and Fj prime, are independent, and also if this set S of cluster centers is relatively large, then the probability with which the 2 points will be separated is close to 1. And therefore, from our perspective, from our model's perspective, this is a completely unfair behavior. Finally, the results of Anderson et al. Include constant factor approximation algorithms for all metric-related objectives. Okay, now let's move on to another concept of individual fairness, a concept which again follows the Dwork et al. Paradigm, but this concept here defines similar treatment in a different way compared to what we saw already. Specifically, this concept defines similar treatment in terms of trying to provide equitable assignment distances to similar points. For this concept, the starting point is an observation that we have made before in the tutorial, and that is that in almost all clustering and facility location applications, the quantity that really matters to a point is the distance to its assigned cluster center. And this quantity, the assignment distance, matters because it corresponds to the quality of service that the point receives. So, as we have said before, in classical clustering applications, the assignment distance corresponds to how representative the cluster center is for the point. And in facility location applications, it corresponds to how far the point needs to travel in order to find its service provider. And the smaller the assignment distance, the happier the point. Okay, suppose now that we are in a situation where we are given 2 points, J and J prime, and let's assume that some higher authority tells us that these 2 points are similar. And let's also assume that we have a solution in which the assignment distance of J prime is much smaller than the assignment distance of J. And I have an example here on the right demonstrating that. So these are our 2 points, J and J prime, and we have a solution which chooses this blue point as a cluster center and assigns both J and J prime there. Again, arrows correspond to us to assignments, and we are in R2 in the Euclidean plane. So you can see that indeed the assignment distance of J prime is much smaller than the assignment distance of J. In such a case, if J can perceive its similarity to J prime, J has every right in the world to feel unfairly treated. And this is because its quality of service is much worse than the quality of service that a similar point to it receives, in this case, J prime. And therefore, with such considerations of fairness in mind, we should have looked for a solution that looks like this, and observe that in this solution, the assignment distances are more or less the same, and therefore, none of the points has any incentive to feel unfairly treated. Okay, before we proceed, I would like to give a more concrete motivational example that demonstrates this sort of fairness consideration. And this is an example that we have mentioned before, but let's revisit it. So suppose that the points correspond to users of an e-commerce website, and let's assume that the metric distances measure how similar the profiles of 2 users are. So the smaller the distance between 2 points, the more similar the profiles of the 2 users. For example, the 2 users may be interested in the same type of products. Now, the goal of the website is to develop a recommendation system. And to do that, the website proceeds in 2 steps. In the first step, the website will choose K representative users, and you can think of those users as the chosen cluster centers. And subsequently, the website will construct an assignment function phi that will map every user to one of the chosen K representatives. Now, let's see how recommendations will be provided by the system. We can assume that every point J every user J will receive recommendations based on the profile of its assigned representative, based on the profile of phi J. And if that's the case, the smaller the assignment distance is for J, the more representative phi J is for J, and therefore the more suitable, the more fitting the recommendations that the user receives in the end. And if there is another point j prime that can be considered as similar to j, and j prime receives a much better, much smaller assignment distance, much smaller than the assignment distance of j, then j would arguably feel unfairly treated because the quality of recommendations j receives is much worse than the quality of recommendations j prime receives. Now, let's see a model, a problem that addresses this sort of fairness considerations. This problem is called alpha-equitable case center. This problem is introduced in a paper that is going to appear at AAAI stats this year. And actually, again, most co-authors of this paper are also organizers of the tutorial. Let me begin by telling you how we defined similarity between points in this paper. What we did was basically assume that for every point, we are given a set Sj, for every point j, we are given a set of other points Sj that contains all points that are deemed similar to j. And we call this set Sj the similarity set of j. I also want to argue that this way of modeling similarity is far easier to handle and construct in realistic applications compared to the approach with the psi values that we have already discussed. And this is because in the approach with the psi values, what you need is for every pair of points to pinpoint an exact value in the 0-1 interval that will tell you how similar the 2 points are. And this is quite the cumbersome task in a realistic application. On the other hand, here with this definition of similarity, all you need is for every point a list of other points that are considered similar to the initial point. Furthermore, in this problem, we are given a parameter, an input parameter alpha, which we assume to be greater or equal to 1. And this parameter will play a very important role later on. Now let's see what the computational goal is. As always, we need to choose a set S of at most k cluster centers and construct the assignment function phi such that we minimize the case center objective. So in this problem here, we only care about the case center objective function, which is minimize the maximum assignment distance over all points. Finally, let me tell you how exactly we define similar treatment. We did that by introducing a novel fairness constraint, and this fairness constraint says that you should make sure that for every point j, and for every other point j prime that can be considered as similar to j, you have that the assignment distance of j is at most alpha times the assignment distance of j prime. And observe that if a solution satisfies this constraint, then the smaller the input parameter alpha is, the smaller the gap between the two assignment distances. I would like to say a few more words regarding this input parameter alpha. As I mentioned, the smaller alpha is, the closer the two assignment distances will be. And let's see some examples. Assume that alpha equals 4. If that's the case, this solution over here to the right might be considered fair, might be acceptable. And this is because the assignment distance of j is at most 4 times the assignment distance of j prime. However, if alpha is smaller, 1, let's say, this solution over here is no longer fair, can no longer be considered fair. And therefore, we need a solution in which the assignment distances are closer. So in the case of alpha equals 1, we actually need assignment distances that are exactly the same. Overall, the main observation is that the closer alpha is to 1, the more equitable, the more fair the solutions we produce. However, the question that naturally arises here is for what values of alpha is this problem even well defined? And by that I mean, for what values of alpha can you even guarantee the existence of a feasible solution? Can you guarantee that there's always a solution that satisfies this fairness constraint? And this is a very crucial question. In the paper, we addressed this question. First, we saw that when alpha is strictly less than 2, there's always a solution. When alpha is strictly less than 2, there exist instances that do not admit any feasible solution at all. However, when alpha is greater or equal to 2, we saw that there is always a feasible solution to the problem, and therefore we settled the important question regarding the regime of alpha, where this problem is well defined. I also want to mention that this transition phase result for alpha doesn't only hold for the k-center objective that we study in the paper. It also holds for k-median and k-means, and this is because this result is a result on feasibility. It doesn't have to do with optimizing some objective. The main result of our paper is an efficient algorithm that produces solutions which satisfy the fairness constraint, and these solutions have objective function cost of at most 5 times R star plus Rm. R star here is the value of the optimal solution, and Rm is the maximum distance between similar points. In the paper, we extensively argue that when the metric distances d are a good approximation of the true similarity relationship for points, in that case, Rm will be close to R star, O of R star specifically, and if that's the case, then our algorithm produces constant factor approximate solutions. Lastly, in the paper, we also saw that with some mild restrictions on the similarity sets, our algorithm produces solutions that also have a bounded price of fairness. And actually, these mild restrictions here are very easily enforceable, and they are enforceable in a way that's very explainable to the points. Okay, now let's switch gears and let's start discussing concepts of individual fairness that do not follow the Dwork et al. Paradigm. The first such concept that we are going to see is a concept that goes by the name of a center in my neighborhood. The starting point here is again a standard K clustering problem, where as always you need to find the set S of at most K cluster centers and construct an assignment function phi such that some metric related objective is minimized. Specifically, in this model, we are interested in objectives that are a function of the sum of the assignment distances, objectives of this form. And observe here that when this parameter p is equal to 1, then we have the k median objective, and when p equals 2, we have the k means objective. These objectives are global objectives over all the points, and in some sense they can be perceived as the average assignment distance that we provide to the points of a data set. The main argument here in this model is that minimizing such a global objective over all the points does not necessarily imply that you satisfy specific needs of the underlying individual points of the data set. And let me give you an example. Recall the vaccination centers application that we have mentioned before in the tutorial, in which we want to allocate vaccination centers in the metric space such that every location has close access to such a vaccination site. Okay, in this application, let's assume that these red points here are part of the input, and let's also assume that this point over here that is in the center of this dotted circle, let's assume that this point corresponds to a senior citizen. It is natural to assume that the senior citizen will not be able to travel very far away in order to find the vaccination center and get vaccinated. And therefore, in the example here, I'm denoting the maximum radius to which this senior citizen can travel. I'm denoting that with a dotted circle around the point. Okay, these are the specific needs of the individual points. However, if on this example, we just run an algorithm that minimizes k-means, let's say, without any further consideration regarding such specific needs, we might end up with a solution that looks like this. And in this solution, we will place a cluster center, a vaccination center on this point over here. And we will have all other points travel there in order to get vaccinated. And you can see that this solution has the senior citizen travel outside of their maximum radius. Therefore, this solution may be considered unfair to that specific individual because it does not take into account their specific needs. And the solution that would have looked something like this may have been much better, and this is because this new solution over here doesn't have the senior citizen travel outside of their maximum radius. Now, in order to formally incorporate such considerations of fairness in the specifications of the problem, we assume that for every point j of the dataset, we are given a value rj that denotes the maximum distance that the point can travel in order to find its cluster center, its service provider. Okay, and we also call this values rj. We also call this value rj the neighborhood radius of j. And now in this model, besides minimizing the global objective over all the points, we want to make sure that in the return solution, the assignment distance of every point is at most the given rj value for the point. This model was introduced in a Force 2020 paper by Jung et al. And perhaps the most important result of that paper is that in this problem, even computing feasible solutions is NP hard. And a feasible solution here is just a solution that satisfies this. Okay. Given this NP hardness result now, if we are still interested in addressing this type of fairness consideration, we should turn our attention to bicriteria algorithms. And an alpha comma beta bicriteria algorithm for this problem is an algorithm whose objective function cost is at most alpha times the optimal cost. And this algorithm produces solutions in which the assignment distance of every point is at most beta times the neighborhood radius of the point. And we need this multiplicative beta violation because of this NP hardness result. Now, after the Jung et al. Paper, there has been a series of works that gave increasingly better results for this model. And by increasingly better results, I mean that these papers kept on improving these parameters alpha comma beta. Initially, there was a paper at ICML 2020 by Mahabad and Vakilian. There was also a paper at NeurIPS 2021 by Chakrabarty and Rahbani. And there is also going to be a paper at AAAI Stats this year by Vakilian and Knittel. Okay, now I would like to discuss a concept of fairness that tries to address scenarios of discrimination against individual points in the context of clustering with outliers. So let's briefly recall what clustering with outliers is. First, as always, you need to choose K cluster centers. However, in this model, you are not required to cluster all points of the dataset, and you can rather choose a set A of points to cluster. And this set A should contain at least M points. M is a given input parameter here. Points that are going to be left unclustered are called outliers. And as we have mentioned before in the tutorial, being chosen as an outlier is an inherently disadvantageous event for a point. In an earlier section, we saw how we can protect against scenarios of demographic bias in the context of clustering with outliers. Now we are interested in protecting against scenarios of individual discrimination, against individual points when clustering with outliers, of course. So the first thing we need to do is identify such scenarios. A moment's thought reveals that scenarios in which certain points are always and deterministically chosen as outliers, such scenarios are blatantly unfair to those points, and they are unfair because they always choose them as outliers. So this is exactly the type of scenario we want to address. And let's see a model that addresses this type of scenario. And a key component of this model is randomness. In this model, for every point j of the dataset, we are given a value pj in 0, 1. And now, instead of just asking for a single deterministic solution, we rather ask for a distribution D over solutions. And we want this distribution D to satisfy the following properties. At first, we want every solution drawn from the distribution to be a feasible solution. That is, we want every solution drawn to have at most K cluster centers and cluster at least M points. More importantly, we want this solution, this distribution, to satisfy this property over here, and this is exactly the property that captures fairness in this model. This property says that for every point j, you should guarantee that the probability with which this point gets clustered is at least the given value pj. Finally, we may also want to minimize some metric-related objective. Observe here that this model indeed addresses scenarios that discriminate against individual points, and it does that by providing to every point a chance of getting clustered, a chance of not being chosen as an outlier. An interesting aspect and the useful aspect of this model is that the values Pj are arbitrary in the input, and this is a good thing because it allows us to capture a wide range of fairness scenarios. For instance, we can capture equitable treatment where we will provide the same Pj value to every point, and therefore we will guarantee that every point gets clustered with probability at least the same value. We can also capture a preferential treatment case where we focus our attention to points that are in a higher need of help. And to those points, we provide a larger Pj value, and therefore we end up clustering them with a higher probability. This problem has only been studied for the case center objective, and it was introduced in Approx Random 2017 paper by Harris et al. The main result of Harris et al. Is a two-approximation algorithm for this problem. However, this algorithm is a pseudo-approximation. And by that, I mean that the solutions of this algorithm may incur a small violation of some of the constraints of the problem. However, later on at TIPCO 2020, there was a very beautiful paper by Aneg et al. That gave a true approximation algorithm for this problem. And the true approximation algorithm is an algorithm that does not incur any violation at all in the constraints. Okay. Now, let's move on to the last concept of individual fairness that we are going to discuss in the tutorial. And in order to motivate this concept, let's revisit an example, a motivational example that we have talked about earlier. So once again, suppose that we have the employees of a company, and suppose that we also have their performance rating in the current year. And let's assume that the company wants to cluster its employees based on their performance ratings and create K clusters, K groups. In other words, here the performance ratings serve as the metric distance. Okay, after the clustering is constructed, the company will decide an ordering on the clusters such that employees in the first cluster will receive the highest amount of raise, employees in the second cluster, the second highest amount of raise, and so on. Okay. In this application now, assume that I am one of the employees of the company, and let's say that I wasn't placed in the cluster that receives the best possible raise. If that's the case, and if the performance ratings and the clusters are public, one thing I can do is compute my average distance to the points of my cluster, and for every other cluster, compute my average distance to the points of that cluster. Now, if there exists another cluster which receives a better raise compared to my cluster, and my average distance to the points of that cluster is smaller than my average distance to the points of my cluster, if that's the case, I arguably feel unfairly treated because on average I'm closer to points that receive better treatment, that receive better raise. And I have an example here that demonstrates this. So we have these two clusters, this one over here to the left and this one over here to the right. And let's assume that this cluster to the right receives the better raise. And suppose that I am the green point. Okay, if this is the Euclidean plane, on average, I'm closer to the points of this cluster and not the points of my cluster. And therefore, I cannot justify the company's decision. I feel like the company should have slightly expanded this cluster and include me there as well. Okay, the formal problem definition now goes along the following lines. We have our input set of points and we need to partition it into K clusters, K groups, such that, fairness constraint incoming, we want for every cluster that we create, and for every point we place in that cluster, for every point J, we want the average distance of J to the rest of the points of its cluster to be less or equal to the average distance of J to the points of some other cluster J prime for every other cluster J prime. This model was introduced in a 2020 paper by Kleindessner et al. And the main result of that paper is that this problem is NP-hard. You cannot decide the existence of such a clustering. You cannot compute such a clustering unless P equals NP. However, the authors of that paper also gave a positive result, and that is when the metric space, when the underlying metric space is the Euclidean line, then there exists an efficient algorithm that can compute the clustering that satisfies this constraint. Okay, so this concludes our discussion on individual concepts of individual fairness and clustering. Thank you very much.